Hey guys, I hope everyone's having a good weekend. Happy Mother's Day. So, this week we're going to be talking about inequalities. So, maybe some of you remember inequalities from foundations. Most of you would have done inequalities first thing last semester in Foundations 11. So, a lot of this might be kind of somewhere in the back of your brains, but hopefully we can bring it forward when we're talking about inequalities this time around. So in the past, we've solved inequalities in one and two variables. We've looked at them both graphically and algebraically, right? So we've talked about linear equalities. So for example, if I had an equation like this or an inequality like this, where I said 2x minus 3 is greater than 13. So what that's asking you to do is asking you to figure out, okay, what value for x is going to make the left-hand side larger than 13? So there's going to be kind of an infinite number of solutions for x because as soon as we figure out, well, what value for x makes the left hand side equal to 13, then any number of values for x that are either larger or smaller, depending on a couple of variables, is going to make this statement true. So if I were to solve something like this, then what I would do is I would treat it just like I would treat an equation, where I'm going to get the x by itself, right? I'm going to take the minus 3 and I'm going to move that to the other side by adding 3, right? So I'm going to add 3 to the left-hand side and add 3 to the right-hand side, and I get 2x is greater than 16, and then divide both sides by 2. So I divide by 2 on the left-hand side and divide by 2 on the right-hand side, and I get x is greater than 8, right? So what that means is x can't be 8, right? If x were 8, that means the left-hand side is equal to the right-hand side. And that's what we're used to. We're used to solving equations where you want to figure out when will one side be equal to the other. But in this case, I don't want to solve the equation when the left-hand side is equal to the right-hand side. I want to solve the inequality. When will the left-hand side be larger than the right-hand side? And that's going to happen when this value for x, this variable that I have here, is larger than 8. And it could be something as small as like 8.00000001, right? As long as it's larger than 8, right? So this is something that we would have talked about in Foundation, something we even talked about in Math 9, Math 10, right? Where we have these inequalities. And we start off by just graphing them on number lines. We say like, well, here's my number line, right? Here's 0, 1, 2, 3, 4, 5, 6, 7, 8, right? And then we have that open circle to say that it can't be equal to 8, but it's got to be larger than. So we use an arrow to say it's going to be greater than 8. Then in Foundations 11, we took it one step further and we said, well, now I don't want just an equation, right? Just an inequality that has like a solution. I want an inequality that has an infinite number of solutions. So now I'm looking at my kind of how inequalities relate to functions, right? So with the previous slide, we talked about how inequalities relate to equations, where I could have something that's like 2x minus 3 is equal to 13, and then solve for x, and I get x is equal to 8. Well, that's an equation, right? And then we talk about equations and we translate those into functions where now I have a line that can be displayed by using this equation. So I'd have something like y is equal to x plus 3. And there's an infinite number of solutions, but all of those solutions fall on the line that would be graphed if we plotted y equals x plus 3. So then I take it one step further and I say, well, let's add inequalities to this. So last semester we talked about how to solve inequalities in two variables, right? Where we would graph this line, y equals x plus 3, and then we'd look at the entire solution region or the feasible region that would satisfy this inequality. And then we would shade that in to say that this entire area above that line, including the line itself, will satisfy this inequality, x plus 3, right? And we did the same thing with uh, less than, greater than, less than equals to, greater than equals to. And we talked about the rules. So, like, for example, if I had greater than or equal to, right, the solution, the feasible region is above my line, and my line is solid to say that it is in fact a part of my solution region, right? But then we also have my less than symbol to say that my line is going to be less than, right? And we have strictly less than and strictly greater than to say that my line is not, in fact, a part of my solution. So we say that by making our line a dotted line, right? So this is stuff that hopefully we should remember from foundations, and if not, make sure that you guys are asking questions on during our live session, or even reach out over Teams. But this is something we did talk about last semester. So this semester, what we're going to talk about is not just linear inequalities. We're going to talk about quadratic inequalities. So we have discussed solving linear inequalities, and now we're going to discuss quadratic inequalities. There are two types of quadratic inequalities: quadratics in one variable and in two variables, just like with linear inequalities, right? So, like if you think about the last two slides we just talked about, the first one only had one variable. It was just an x, and that x had like there was a number on one side, right? So like we think about equations versus functions, right? With an equation, there's an answer. With a function, there's a line that gets graphed, right? Same thing is true for quadratics. With a quadratic in one variable, there's going to be an answer. With the quadratic in two variables, that's a function where it's something that we can graph. Well, the same thing is going to be true for inequalities, right? So if I have an inequality with one variable, we're looking for some descriptor of, well, what are the answers? And then with an inequality in two variables, I'm looking for a graph, some kind of region that's going to satisfy this answer that we can show visually by graphing the thing. So let's start off with one variable, and then we'll move to two variables next. So to figure out a quadratic inequality in one variable, there's two strategies we can use. We can either try to graph it and see when it will satisfy this restriction, or we can look at the roots. And either way, we're going to be looking at the roots. Just one, we're going to do it more visually, and the other one, we're going to do it more algebraically. So if I had, say, this quadratic inequality here, where we had x squared minus 3x minus 4, what we're going to do is we're going to take a look at when is this thing greater than 0, right? That's what we want to figure out. But in order to do that, we have to decide, well, where is it 0? Because once we know where it's equal to 0, then we're going to know where it makes the shift from being greater than 0 to less than 0, or makes the shift from being less than 0 to greater than 0. And then we can do that with these two strategies. So first off, graphing. To solve by graphing, what we're going to do is we're going to first off graph the function. Then on our graph, we're going to find the roots. We're going to say, okay, well, now here's my graph. So where is this thing equal to 0? And it's equal to 0 here at -1, and it's going to be equal to 0 here at +4. Then we're going to take a look at, well, now that I have the graph of my function y is equal to x squared minus 3x minus 4, when is my graph, when is this line greater than 0? So 0 in this case takes the place of the y, meaning that I'm looking for when is this graph above my x-axis, or in other words, when are my y values positive? And they are positive in this part of my graph here, and in this part of my graph here. So the answer I'm looking for with a question like this is I want to describe the x values that make my y values positive. So if I took a look at my left-hand side over here, how would I describe these x values? So for example, x equals -1 is not a solution because that's where it's equal to 0. And I'm looking for the numbers that are strictly greater than 0. But x equals -2, if I were to take a line and draw it straight up from -2, we'd see that it does in fact pass through my graph up here at some positive y value. And if I did the same thing for -3, again, it would pass through my graph at some positive y value, and -4, -5, and -6 would do the same thing. And the same thing if I come to the right-hand side. Here at 5, if I were to draw a vertical line straight up, it would pass through my graph at some positive y value, and then 6, and 7, and 8, and 9. So what we find is instead of having two answers like we would normally would, like if I had a quadratic equation where I said x squared minus 3x minus 4 is equal to 0, and we would try to solve that, instead of having just two answers, I have two boundaries where my answers aren't equal to these numbers. They are set to the left and right of those numbers, or those numbers are set more as boundaries than answers. So for this graph, we said that our intercepts were -1 and +4. So before we get to the -1, right, when we're to the left, so if we were to go from the left to the right, so if I were to kind of think about it going from the left to the right, before I get to the -4, I have answers that work, right? I have this area over here that has answers that work. Then, as soon as I pass through this x equals -1, I dip below my x-axis and I have answers that no longer work anymore because now these are less than 0, which don't satisfy this inequality that I'm trying to solve for, right? And then from -1 to +4, and then when I pass through +4, again, I've got answers that work. So over here, I've got answers that now work. So before -1 and after 4, the function is positive. So we can write that in a couple of different ways, right? So we can use our inequality symbols to say that -1 is, um, sorry, x has to be less than -1 and x has to be greater than 4, right? Because those are the regions of our graph that work, right? So if I'm thinking about here, x has to be less than -1 because those are when I get positive y values, or x has to be greater than 4 because those are when we get positive y values. But another way to describe that are these brackets here, where I've got this statement right here. And what this statement says is that x is an element of some group. So what we're saying is this statement after my little e symbol here is how I describe x. So there's two types of brackets that we're using here. There are square brackets and there are round brackets. The square brackets mean greater than or and equal to or less than and equal to. The round brackets mean strictly greater than or strictly less than. So what this statement is saying is that x is an element of this group where we go from -infinity, this number that's so infinitely negative that it basically takes up every single number in the negative direction, all the way till -1. And then it stops. But it's not equal to -1, so we're going to use a round bracket. And we can never be equal to infinity, so again, we describe that using a round bracket. And then this bracket does the same thing where we start at 4 and then we go off infinitely towards the positive numbers. And again, we're going to use round brackets on either side to say that it's not equal to, it's just strictly greater than or strictly less than. And then this symbol in between, this U kind of looking symbol here, is the union, is what it stands for. And that says that it's this group of numbers and this group of numbers. That's where X kind of falls. Those are the possible answers for X. So let's take a look at an example here. And if at this point in time you feel like, you know what, maybe I want to try this, maybe pause the video and give it a try. And then once you're ready, restart it and we'll take a look at how our answers compare. So to graph this thing, again, what we're going to want to do is just find some key pieces of information. So for example, I want to figure out where are my x-intercepts, where are my y-intercept, and then go from there. So my x-intercepts, to factor this, we're looking for two numbers that add to give me -6 and multiply to give me -5. So that would be x minus 5 and x minus 1, right? So it means I have an x-intercepts at +1 and +5. So 1, 2, 3, 4, 5. I have an x-intercept here, and I have an x-intercept there, right? My y-intercept is the c value, so I have a y-intercept up here at also +5. 1, 2, 3, 4, 5. We'll make that a little nicer looking. 5. Right, so up here at 5. So now if I were to graph this, and just we don't necessarily need a perfect graph here, right? Because we're not worried about graphing this thing. We're worried about solving the inequality. So really, all I care about is when is this thing less than 0, right? That's what I'm trying to do. So now that I have this graphed, when is this less than 0? That's what we're trying to figure out. So looking at my graph, when are the numbers, the y values, negative? And they're negative between my two x-intercepts. So if I were to go from left to right, just like before, what I find is that numbers that are less than 1, we have numbers that are greater than 0. So that doesn't satisfy my inequality that I'm trying to solve for. Numbers that are between 1 and 5, oh, yep, those are less than 0. So that's kind of the area I'm looking for. And then numbers that are greater than 5, again, are more than 0. So they don't satisfy the inequality I'm solving for. So the answers here are x is an element. And again, I'm going to use round brackets because I'm strictly less than. So I don't want the numbers themselves because I don't want them to be equal to. But there's an element of the numbers from 1 to 5. And that's it. That is my solution, right? No infinities, no negative infinities, because it is completely sectioned off by this x-intercept to this x-intercept. That small region is where my solutions are. Okay, so the other strategy we have is to use roots and test points. So instead of looking at my graph and trying to figure it out from there, what we can do is we can just look at the roots, just look at the x-intercept and say, okay, well, what happens on this side and what happens on that side? So to do that, what we're going to do is, first off, we're going to factor, or we're going to use the quadratic formula. We're going to figure out where are the roots. Then we're going to write a number line, right? We're just going to have a line, and we're going to say, here's root number 1, here's root number 2, and we're going to place those on the line, right? So we're just going to have some number line going to the left and the right, and on my number line, I'm going to say, okay, well, there's root 1, and there's root 2. Then we're going to use test points. So we're going to say, if this is root 1, let's test some number that is smaller than root 1. Let's test some number that's in between root 1 and root 2. And let's test some number that is larger than root 2. Right? So we're going to test 3 numbers and say, okay, well, let's test one that's smaller here, in between the two of them, and then larger than the other one. And then we're going to substitute each test point into our equation to say, okay, is this greater than 0 or is this less than 0? So, for example, again, if we go back to the one we talked about originally, so let's take a look at this one and let's factor it, right? So we have x minus 4, x plus 1, right? So my roots are x is equal to 4 and x is equal to negative 1. So if we talk about our number line here, right? So we have our number line where the first root is negative 1, and then we have another root that is positive 4. So we're going to test these regions or these sections of my number line where I have numbers over here that are less than negative 1. So for example, negative 2. I have numbers over here that are in between negative 1 and 4, so possibly 0. And I have numbers over here that are greater than 4, so 5. And again, I don't necessarily care about what these numbers are going to be equal to when I plug them into my graph. All I care about is, are they larger than 0 or less than 0? Right? So I take this negative 2 and I plug it back into my original equation to see what answer am I going to get. Now, you can either plug it back into the equation you started with, or you can plug it back into the factored form, depending on what's easier. A lot of the times, the factored form is actually going to be the easier one to plug it into, and we'll see an example where it's not here in a second. So if I take this negative 2 and I plug it back into the factored form, I get negative 2 minus 4 and negative 2 plus 1. Right, so if I go through my order of operations here, so negative 2 minus 4 is negative 6, and negative 2 plus 1 is negative 1. So negative 6 times negative 1 is positive 6. Right, if I do this, so over here, on to the left of my negative 1, where I got this negative 2 from, I get positive numbers. Right, do the same thing from negative 1 to 4. So if I check this 0, and 0, a lot of the time, the easiest place to plug the 0 in is to the first equation, because this first term becomes 0, the second term becomes 0, and my answer here is negative 4. So in between my two roots, I get a negative answer, and then do the same thing to the right of my larger root. So I take that 5 and plug it into my second equation here. So 5 minus 4 and 5 plus 1. So 5 minus 4 is 1, and 5 plus 1 is 6, and 1 times 6 is 6, and I get positive solutions. So now that I know that my answers that are less than -1 are positive, my answers that are between -1 and 4 are negative, and my answers that are greater than 4 are positive, where do I have answers that satisfy this inequality? Or in other words, where do I have answers that are greater than 0? And I have them here and here. So again, what I would do is I would describe that by saying x is an element of the numbers from -infinity to -1, union with the numbers from 4 to infinity. So exactly the same answer that I had when we were looking at the graph, but just a different strategy to get those numbers. So let's take a look at a couple more of these examples. So here's one, similar idea where I have some inequality where my a is 1, so I still am dealing with this a of 1. But now I'm looking for numbers that are less than or equal to 0. So we can use either strategy. We could try to graph it, or we could just look at the roots. Either way, we're going to want to find the roots, right? Whether we're graphing it or we're just looking at the roots specifically, we're still going to want to find the roots, because to graph this inequality, we need to know where the roots are and the inequality. So always a good first step is to factor. So let's factor this right now. So we get the function y equals x squared minus 2x minus 3. If we're going to graph it, right, that's the graph we're going to look at. If we're not graphing, if we're just looking at the roots, then we could just deal with the expression x squared minus 2x minus 3. But either way, let's take a look at how we factor this thing. So we're looking for two numbers that add to give me -2 and multiply to give me -3. So we get x minus 3 and x plus 1. So that means I have x-intercepts at x equals 3, and I have an x-intercept at x equals -1. Right? So again, whether we're graphing or we're looking at the roots, we're still going to kind of deal with this the same way. So let's graph it just to take a look at what this thing's going to look at. So if we have an x-intercept here at -1 and an x-intercept at 1, 2, +3, right? We have a y-intercept here at -3. We know that this graph opens up because the a value was positive, so that makes sense that our graph would go down like this. So now let's go back to our inequality and make this decision. When is this function less than 0? Or in other words, when is it below my x-axis? When will I have negative y values? And I have negative y values in between my two roots, right? So over here, when I have numbers that are less than -1, I'm positive, so that's not going to work, right? When I have numbers that are greater than 3, I'm also positive, so again, that's not going to work because I'm looking for numbers that are less than or equal to 0. So in between my two roots is where I will find my solution. So again, the way that we're going to describe that is x is an element, but this time, because we have that equals to symbol, we're going to use our square brackets to say that it can be -1 and it can be 3. So they are the numbers between -1 and 3, but they also include -1 and 3. Okay, so now let's take a look again with numbers that don't have a positive a value. Maybe it's some different a value, and we should have an idea of how to deal with this, right? What does a negative a value do? It just takes my graph and it makes it open down. So what does that mean, right? Previously, when we were opening up, we had this pattern where it was like um, positive on this side of my root, positive on this side of my root, negative between them. So whether I was looking for numbers that were larger than 0 or less than 0, I could find them. Right now that I'm dealing with a negative a value and I open down, those are going to change. So it might change the way we look at this. So again, to deal with a question like this, what we're going to want to do is, well, let's figure out where the roots are. And to do that, we're going to factor. And the first step of factoring is to factor out this negative. So we're going to say that negative, and on the outside, x squared minus x minus 12. So now we're looking for two numbers that add to give me -1 and multiply to give me -12. So the negative's still there, and we get x minus 4, x plus 3. So that means I have x-intercepts at 4 and x-intercept at -3. So now if we take a look at the number line this time, right, if we take a look at this idea of using the number line, we have an x-intercept at -3 and we have another one at +4. So now we have to check numbers that are less than -3. So for example, -4. Numbers that are between -3 and 4, so 0, and numbers that are greater than 4, 5. So now at this point, what we're going to want to do is we're going to want to test those numbers to see, well, when will they be positive and when will they be negative? So again, the idea here is we can either plug it into my original function or I can plug it into my factored form. But if you plug it into your factored form, don't forget that this negative was out front here. So when you go to plug it in, you're going to take the negative. So if I take this -4 and I plug it into my factored form, I get the negative of -4 minus 4 and -4 plus 3. So we get the negative of -4 minus 4 is -8, and -4 plus 3 is -1. So the negative of -8 times -1 is -8. So on the left of my -3 here, I have negative answers. And possibly at this point, you're starting to recognize that there's a pattern where since we're dealing with a parabola, and a parabola kind of follows this shape where it will hit my x-intercept, dip below it, and then move back up. So we have positive, negative, positive. Or if it's upside down, we'll do the opposite where it goes negative, positive, negative. You could probably figure out that if this one was negative, my next one's going to be positive, and then this one's going to be negative. But let's check to make sure, right? So let's try 0, and let's plug 0 into my function and see what we get. So if I plug a 0 in for x squared, I get 0. If I plug a 0 in for x, I get 0. So 0 plus 0 plus 12 is 12. So I do, in fact, get positive. And then again, let's try this 5 and plug it in. So again, I have the negative of 5 minus 4 and 5 plus 3. So I have the negative of 1 times 8. And 1 times 8 is 8, and the negative 8 is, in fact, negative. So now, where do I have answers that are less than 0? I have answers that are less than 0 outside of my -3 and outside of my 4. So numbers that are less than -3 and numbers that are greater than +4. So we'd say that x is an element of the numbers from negative infinity to -3, and then it stops, right? It stops being negative when it hits that -3, and from 4 to positive infinity. Okay, so just because we've been looking at quadratics where they're less than 0 or greater than 0 doesn't mean that's always going to be the case. Sometimes they can be mixed up and moved around. We could have x's on both sides. We could have x squareds on both sides. It could be equal to greater than numbers that are not 0. We're still going to deal with these exactly the same way we would have dealt with any quadratic. And what I mean by that is if I gave you a quadratic, if I said like x squared plus 3x is equal to some number, whatever that number might be. So, for example, 18, right? We never just leave it like that. We always take the number, move it to the other side, and set it equal to 0. Because once it's equal to 0, then we have a number of strategies that we can use to solve. The same thing is true for inequalities, right? So if I gave you something that was like this one, where I had 2x squared minus 7x is greater than 12, I don't like that 12 being there. So the first thing you have to do when you're doing a question like this is take that 12 and move it to the other side. So we get 2x squared minus 7x minus 12 is greater than 0. And again, what we're going to do at this point is solve it just like we solved the previous inequalities. And I'm going to leave it there. I want you guys to try this. And if you're still struggling, you're still having issues, make sure that you're coming to the live sessions on Thursday and asking questions. But we would solve this exactly the same way. There we're going to graph it, or we're going to look at the roots and test points. Okay, so here's just one more question that maybe you guys want to try. So a couple of questions for you to try. See if you can't figure out where this gives an answer that's greater than 12 and where this one would give an answer that's greater than 10. I will hopefully see you guys on Thursday. Have a great night, and hopefully you all had a great Mother's Day.